The following topic is about resonant antenna. The resonant antenna is one of the antenna clusters covered in this course, BEE 4433 Antenna Theory and Propagation. This type of antenna resonates well at a single frequency band and suits very much to applications that has specific single frequency. While this kind of antennas has real input impedance, they however comes with a trade-off in the frequency bandwidth and having low to moderate gain. Throughout this session, we will look into two types of resonant antenna, namely Yagi and Microstrip Antenna. Yagi antenna is a directional antenna consisting of multiple parallel elements in a line made of metal rod. There are three elements that make up a Yagi antenna. A single driven element connected to the transmitter or receiver with a transmission line. Parasitic elements which are conductors but are not connected to either transmitter nor receiver. These elements is known as reflector and directors. And a perpendicular structure that holds up these elements, known as boom or crossbar. This structure is made of non-conducting materials. The construction of the driven element is similar to a dipole system. The driven element is connected to a balloon and a coaxial cable. Balloon is also known as a balanced and unbalanced unit. The guide for Yagi design takes into consideration the following parameters: the length of the driven element, reflectors and directors, and the spacings between directors, reflector dipole, dipole director. Unlike the dipole antenna, Yagi antenna exhibits directional radiation and it is pointing in the direction of the directors. The radiation directivity is influenced by the number and size of the directors. Let's delve into the details of the operating mechanism of a Yagi antenna. Operates as a typical dipole system. The alternating currents in the driven element generates radio waves. Radio waves from each element are emitted with a phase delay, so that the waves are emitted in the forward directions are in phase. Therefore, the forward waves could be added up together, resulting in enhanced power in the direction. This is termed as constructive interference. On the other hand, the reverse directions are out of phase, causing the wave to cancel out each other, hence reducing the power emitted in this direction. This is termed as destructive interference. Manipulation of this wave is achieved by adjusting the dimension and structure and the placement of the directors and reflectors. The length differences and position influence the impedance and reactance of the antenna and causes phase lags. Let's analyze the performance characteristics of a Yagi antenna that I have simulated earlier on. Operates at a Wi-Fi frequency range, 2.4 GHz. The antenna exhibits a very narrow band frequency response, as approximately 12 MHz, equivalent to 5%. This antenna has an omnidirectional radiation with a half power beamwidth of 65.1 degree. The antenna is linearly polarized, as the axial ratio is far beyond 3 decibel. For a Yagi antenna, the radiated gain is proportional to the number of elements, and the size is inversely proportional to the resonant frequency. Next, we will look into microstrip antenna. Microstrip antenna is amongst the most popular antenna used in portable devices due to its design flexibility and low profile characteristic. Microstrip antenna is also known as printed antenna and usually means that the antenna is fabricated using microstrip techniques on a printed circuit board. They are most widely used at microwave frequency range. The structure of a microstrip antenna consists of a radiating patch, ground, and a substrate. Both radiating structure and ground are made of conductors. These two structures are bonded with a dielectric substrate. The patch comes in various shapes such as rectangular, square, circular, annular ring, elliptical, and triangular. The shape influences the operational and radiation characteristics of the antenna. The middle substrate layer carries the properties of permittivity and permeability, which has the effect to the antenna performance. Thick substrate with low permittivity results in better efficiency, larger bandwidth, while thin substrate with high permittivity reduces the size of the antenna, but with a trade-off of greater loss, less efficiency, and smaller bandwidth. The ground houses the feeding structure of a microstrip antenna. There are 4 techniques which are typically adopted in a microstrip antenna, which are inset feed, coaxial cable, coaxial feed, aperture couple, and proximity couple. Customization in microstrip antenna design include bandwidth improvements, miniaturization, and polarization. Another phenomena that is related to microstrip antenna designs is fringing effect. Fringing happens due to electric field lines, which makes the antenna size wider after excitation. The main cause of fringing effects is due to the width and positions of feet in the antenna. The effective dielectric constant is introduced to account for the fringing effect and wave propagation in the line. There are 3 methods used to estimate the performance of a microstrip antenna, namely transmission line, cavity mode, and full wave. In this session, we will look into the transmission line model for a rectangular patch microstrip antenna. Critical dimensions for the antenna include dimension of the patch, the length and the width, substrate height, and dimensions of the ground, length and width. This analysis is done with 2 assumptions. The ratio of patch width over height is much greater than 1, and dielectric permittivity is more than 1. Dimensions of the antenna are calculated as follows: the patch width, the effective permittivity, the effective length, ground plane dimension. The transmission line equivalent circuit model is as shown here, and the values of impedance and reactance is calculated as follows. This graph shows the effect of different effective dielectric constants to the performance of the microstrip antenna. Let's analyze the results of a microstrip antenna simulated earlier. The patch operates at 2.4 GHz and exhibits very narrow operational frequency band, approximately 1.5%, which is equivalent to 20.34 MHz. The antenna radiates a unidirectional radiation pattern. The performance of a microstrip antenna depends on patch length, substrate height, substrate permittivity, and patch width. Throughout this session, we had looked into 2 types of resonant antennas, namely Yagi and microstrip antenna. While this antenna exhibits directive radiation, they only operate well at a single frequency narrow band. In the next section, we will look into broadband antenna design.